Swayam Prabha. Digital India. Educated India.
Okay, so I will just summarize the steps in the vibration analysis that we discussed. Obviously, the first step is to get a physical dynamic system to be converted. All right, so let us take a brief overview of the analysis process for any vibratory system, and that is what we discussed, that the first step would be to convert the physical system into its simplified vibratory model as a first step. This vibratory model will be used to derive governing equation of motion. So, the route for doing that, the simplest and the commonly followed is a Newtonian approach, where you get a free body diagram of this vibratory system, and then using Newton's second law get the governing equation of motion. So, that is the step number 2 that we follow, and the next obvious step is finally to get the response, vibratory response from this governing equation of motion through solution process. So, in the mathematics we have a very standard approach of solving ordinary or partial differential equations. In this case, for a discrete system we get ordinary differential equation, and that you solve to get the response x as a function of time. And once we do that, we can represent this response in different formats, and once we represent it, the last step in the vibration analysis is to make sense out of the output that you get through this solution process and relate it to the context of the mechanical design. And this actually is the total vibration analysis process that we typically follow for all mechanical systems. So, apparently it looks very simple, but we discussed that the first step itself is challenging to get any mechanical system represented in a vibratory system or a vibratory model, and rest of the process then becomes simpler. The last step needs you to have a thorough understanding of the vibration phenomena, and that is where we are going to focus on all of these steps in solving several problems in this particular course. So, having given you an overall background of the importance, the significance of vibration engineering, the implication of not following vibration based design, of untimely failure, and in not a robust design, and so on. We have seen several issues associated with the vibration analysis. All right. So, with this objective in mind, the overall content of this course as have been identified in different topics. So, we will get started immediately after this on the discussion of the simplest vibratory model, which is like a single degree of freedom system. How do we model it, how to get the governing equation of motion, how to find natural frequencies, and of course, the next logical step is to get vibration response of such systems when it is subjected to some initial conditions. So, that is essentially a free vibration response of a simplified vibratory model. The first topic is this. The second topic, we will bring in damping in the model, and we will basically look at the single degree of freedom system both from the undamped free vibration response as well as damped free vibration response. But in the topic of vibration damping, I will expose you to different kinds of damping and how those dampings are included in the mathematical model, and what is the difference in the response of different kinds of damping, and how to practically measure the damping or assess the damping, which is one of the most involved or a process that involves a lot of uncertainties. So, we will look at damping little more closely in the second topic, although in the first topic itself we will introduce the basic vibration damping actually. Then we shall have a look at the response, vibratory response of a mechanical system to different kinds of excitation. So, we will begin with an excitation called arbitrary excitation or response to sort of transient excitation. And when you do that, the example would be that if this vehicle is moving over a straight road profile and suddenly it goes through a ditch or a pit on the road, this is typically can be treated like an arbitrary excitation, the profile of which is arbitrary, cannot be captured in a standard mathematical form. So, we shall have a look at, so we discussed that this automobile with a rider can be modeled like a vibratory system, simple vibratory system. So, the first topic will deal with finding out the natural frequencies of this particular system, and suppose this vehicle is subjected to sudden excitation at t is equal to 0, what is the ensuing vibration response as a free vibration response. Whereas, in the second case, when we look at the response to arbitrary excitation, what is going to be the response after it encounters this kind of a road profile, which is sort of a transient in nature, in the sense that it exists only for a short period of time. Once it goes through this kind of a profile, what is the response after it goes through it? That is going to be the topic number 3. After we finish with this, we shall look at other kinds of excitation, primarily the harmonic excitation. So, for example, as we know that there is an IC engine sitting here on the chassis, and as the engine operates, it rotates and then unbalance in the engine, essentially the crankshaft will have excitation generated, and that excitation can be approximated as a harmonic excitation. Any rotating system will have unbalance as the primary source of excitation. So, that excitation can be modeled like f cap cos omega t, where f cap can be m e omega square, that is the unbalance force. So, a harmonic excitation when applied to a vibratory system, how does the response look like and can be estimated, is something which we will learn in this particular topic of harmonically excited vibratory systems. But at the same time, as you might have learned in the kinematics and dynamics of machinery, theory of machines, that a typical IC engine does not strictly generate a harmonic excitation. So, there is a secondary unbalance force and secondary unbalance moments which are generated due to the action of this kind of a slider crank mechanism. So, the excitation is strictly not a harmonic one, but it is a periodic one containing multiple harmonics or more than one excitation frequency. In fact, the sawtooth excitation that I talked about is actually a periodic excitation, and therefore, the response to a vibratory system to such periodic excitations is important to analyze. So, although the harmonic excitation is more common and is readily is an excitation mechanism which is more often seen in practice, periodic excitations are also not rare. So, it is important for us to look at how periodic excitation can be accounted for in the governing equation of motion, and more important, how to find the response to such kind of periodic excitation. Once we have seen these two kinds of excitations, we shall also look at an important topic of transmissibility, which actually means that if I have a profile of the road here, which can be modeled like a harmonic one or a periodic one, the excitation to this vibratory system that we discussed, this excitation will come from the ground, and if this is quantified by capital X, or it is the amplitude with which the road profile is encountered by the automobile, then how much of this X gets amplified or reduced at the chassis level. So, if the chassis vibrates with y amplitude of vibration, how much is y over x, and that ratio is what we call as the transmissibility. So, if we really want our suspensions to be designed in a way that the rider is feeling comfortable in terms of its ride quality, then we would definitely like that this y should be as low as possible for a given value of x, right. So, the transmissibility, in this case called displacement transmissibility, should be as low as possible, so that irrespective of the undulations on the road profile, the vibration or the dynamic response at the seat level or at the chassis level is as low as possible. On the contrary, many mechanical systems like engines or compressors, particularly in a vehicle like a car, we have engines which are mounted on the chassis. So, they are isolated by engine mounts, and when the engine is operating, it generates the excitation force, and that force gets transmitted through these engine mounts to the chassis. Okay. So, in this case, it is the force which is generated here, which if I call as F e, how much of that force is actually getting transmitted to the chassis. Okay. And if we want our mounts to be efficient and effective in reducing the forces which actually excite the chassis to vibrate, we would like these mounts to be designed in such a way that only a fraction of the excitation force from the engine gets transmitted to the chassis. So, those are the ratio F e over F c in this case becomes the force transmissibility. So, all of these concepts are very important from the sound design of the isolation system in any vibratory system, and therefore, this topic is very important to understand, and we shall see what parameters govern the value of this transmissibility and how to design the spring and dash parts in order to have the least displacement transmitted or least force transmitted. Okay. So, this is another important topic that we are going to study in the single degree of freedom system forced vibration response. Okay. And the important insights which are developed through this applies to most complex systems as well. So, it is usually important in that context to understand the single degree of freedom system very well, because the concepts and the insights developed through single degree of freedom system actually apply directly, indirectly when we are dealing with many degrees of freedom. So, even the most complex systems, when you model them with multiple degrees of freedom, you would observe and realize later that the concepts learned from the single degree of freedom system analysis actually comes very handy and useful in understanding the complexities of multi degree of freedom system, and that is precisely the reason why all the introductory textbooks on vibration or even in the advanced level textbooks as well, they devote sufficient space in the book in dealing with the single degree of freedom system. So, it is not that you although practical systems are more complex than what we model them as, it is imperative and important to understand single degree of freedom system inside out. So, I shall devote sufficient time for single degree of freedom system, so that the subsequent discussion is properly followed. The next topic is going to be like migrating to more than one degree of freedom system, and I think we discussed that this automobile, as we see a vehicle with the rider, we model like a simple mass with a spring and a dashpot in parallel as an initial level model, but we also discussed that the same system can be modeled by a system wherein the front and the rear axles suspensions are independently modeled as two separate entities. And in addition, because we might be also interested in investigating the pitch motion, which is quite often possible to get excited because of variety of reasons. So, not only a vertical bounce motion in the form of x of t is important to consider, but also the pitch or rotational motion of the same chassis mass will also be an important degree of freedom to account for, and therefore, we may even model this system as 2 degree of freedom system, x and theta being these 2 degrees of freedom. So, please make a note that even if the mass is a solitary mass here, but the degrees of freedom can be more than one, and we all know that a point mass can have 3 degrees of freedom, that 3 translationals, and if we account for a mass with a size like a chassis, it will also have 3 rotations. So, associated with it are the 3 inertias, and then you can have the same inertia to have 6 degrees of freedom in space, and which will be the 6 degrees of freedom of this system. But if you want to limit yourself in a planar vibration or a planar dynamics, then x, theta, maybe y if required later, you can have these 3 degrees of freedom for sure for analyzing this motion. So, what happens when we migrate from a single degree of freedom system to a 2 degree of freedom system? That is precisely what we are going to learn in this particular topic of 2 degree of freedom system. Things such as mode shapes, which are not relevant or discussed and does not exist actually in a single degree of freedom system, will be introduced to you through a formulation of a 2 degree of freedom system, how to find the natural frequencies and mode shapes, what is the relevance of the mode shape, why are they important, and those things will be obviously discussed in this particular topic. In addition to these 3 aspects in a 2 degree of freedom system, we will also extend the analysis to a force vibration response of a 2 degree of freedom system, how to find the response if this again if this engine is generating an excitation force, then what is the governing equation of motion, how to find the response to such kind of a forced vibration excitation generating the forced vibration is what we will be discussing in this topic, and a natural follow up for that topic is the design of vibration absorber, which also is a very important topic from the context of vibration control. So, we shall have a look at the design aspects of vibration absorber, what are the parameters which are important, how the typical practical vibration absorbers are designed, all of that we will be discussing in this topic. Followed by this, we shall go to and have a look if 2 degrees or 3 degrees are not enough for a practical vibratory system, how to formulate the governing equation of motion for multiple degrees, which means that going in far beyond 2 or 3 or 4 of them. In this particular topic, when the degrees of freedom substantially multiplies and increases significantly, the efficiency of solution process is important. Typical discretized numerical models such as done through the finite element approach will have several thousands of or several tens of thousands of degrees of freedom, and then solving them becomes a challenge. And so, modal analysis is an approach which helps you to efficiently solve these matrix equations, and so we shall see how modal analysis as a process is applied to multi degree of freedom system and eases the solution process and the computational complexity of it. So, once we are done with this, we shall move to another topic which is called as the transfer matrix method. Of course, this method is a competitor to the finite element method, but computationally this is much more simpler and easier to apply. So, we shall have a brief look at the transfer matrix method for solving vibration problems. The natural consequence to this is a continuous system. So, for example, if we have if you want to have an example of a mechanical system, maybe a turbine rotor blade which is a long one and is a tapered one. So, it is difficult to discretize this and lump the masses in different elements separated by the spring and so on. So, when the system is having a distributed mass and stiffness properties, lumping the mass elements separately or mass properties separately and separating them out with stiffness elements is inappropriate, to say the least. It is not that it cannot be done, but then it is more appropriate to analyze such systems with distributed parameters in the formulation of treating it as a continuous system rather than a discrete system. Although there are some problems or challenges in dealing or in formulating a system as a continuous vibratory model or a distributed parameter model. So, this analysis is limited to simpler geometries, but still it has its own significance of analysis in that the solution is exact and is often used for benchmarking an approximate numerical methods analysis results. So, we will have a slightly less involved attention to this particular topic, but we shall still devote time for understanding what a continuous system model is. So, obviously, the way discrete system models generate ordinary differential equation, the continuous system will generate a partial differential equation as a governing equation. Well, the other example in this case is a guitar string. Here also we know that a guitar string is constant diameter stretched wire, and it is a classic example of treating that system as a continuous system rather than a discrete system in terms of its model. So, this is the penultimate topic in our study. The last topic which I will take in this case is random vibration, a very brief introduction to random vibration, and of course, for example, in this particular case the road undulations that we talked about, we modeled it as a harmonic or periodic road profile, but we all know that the road profile is never a harmonic one or a sinusoidal one. Typical road profile is going to have undulations that are strictly random in nature. So, what happens if that kind of an excitation is given to the wheels, what kind of response do we get? So, that is the random vibration for us, and before closing, we will have a brief introduction to vibration measurement process and condition monitoring as the last couple of topics. Of course, the main focus is going to be on all these topics which are very fundamental, important to know in more detail, and these are basically going to be dealt with little lesser in detail, but we will give a glimpse of what these topics are and what you can dig deeper once you are done with this basic understanding. Okay. So, this is the overall overview of this course, and before we start with the nitty-gritties of the single degree of freedom system, maybe we will have a list of recommended books. I have listed these, and then if you really see the literature, there are absolutely no dearth of excellent quality books in the open literature. You will find literally several dozens of them, and but the ones which I would probably refer more often than not are these 3 books. You can, I mean, you are free to use any book in that sense, but primarily I shall stick to some of these books. So, let us talk of a single degree of freedom vibratory system. As the vibration analysis process, we all know that for solving any vibratory system model, we first have to capture the system, the physical system, into its simplified vibratory model. So, one example that I am taking here is that of an electric motor. You all have studied in electrical engineering first introductory course that you in the electric motor there is a rotor which spins in the field of electric field of the stator winding, and the rotor is having these laminated strips here which are forming a rotor, and then they are basically mounted on a shaft. The shaft is supported on the bearings. So, you can see that these are the 2 bearings on which this rotor is supported, and the outer race of this bearing is firmly held in the stator frame. Okay. So, under the electromagnetic field, the rotor spins at a speed constant depending upon the electric field applied, and so on. So, if I want to model this as a vibratory system, as a first approximation, I may assume that this is absolutely rigid, and if this is treated as rigid, the vibratory system schematic of it can be a rotor which is having a mounted rotor, and the shaft is supported in these 2 bearings as I showed you in the picture here, and that becomes the first level schematic. It is a very simplified model, but to start with we can get started with this type of a model. Now, this schematic is not a mass spring and so on. So, how do we model it as a vibratory system? So, for vibratory system we know that we either have to take some inertia and then look at where the springs are located, what elements of the actual physical system can be treated like a spring, and where is the dashpot, and so on and so forth. So, in this case maybe what we can do is that the entire mass can be treated to be lumped at this point of the rotor. So, the rotor itself would be our inertia element. So, that is the mass, and then this shaft can be treated as a flexible element in the entire vibratory system. And it is quite obvious that if the bearings which allows only this degree of freedom, the rotation about its own axis, and restrains the motion in all other degrees of freedom, then and if the bearing is treated as rigid enough, then the shaft is the only one which will provide us the compliance or the flexibility. So, I can for that reason find out from my strength of material understanding a a beam which is simply supported at both ends and mass at the center or the force at the center, I can figure out what is the stiffness of this shaft, and we know that the stiffness of such a shaft with centrally applied load is given by 48 EI over L cube, right. So, L is the length between the bearings, EI is the flexural rigidity of the shaft, which can be obviously a circular shaft. So, you can find out all these values and find the K that is basically representing the stiffness of the shaft. I can find out the rotor mass, and I can lump that mass as the mass being supported by the two bearings. Damping at the moment we will not pay too much of attention, but this damping can be very little or very small. The bearings, rolling element bearings as they are used typically in this case, they offer very low damping, but we can treat some very low level of damping coefficient here if at all. Okay, so, the simplified model then turns out to be a spring mass dashpot system, and that is what we know, that it is a typical single degree of freedom system with this kind of vibratory elements identified. Okay. Now, this is all with our understanding and our knowledge of this particular system, that we are saying that the shaft is treated as the most flexible element in this particular case, but you may as well see, and someone may question that the shaft appears to be reasonably small in length, and have we checked whether really the bearings here are that rigid that we should treat the bearings to be rigid enough and the shaft is flexible enough. Okay. So, if we find out really the shaft diameter and the length are such that the stiffness that you can evaluate from this, if it is small enough compared to the stiffness of the bearing, then of course, this model works proper. Okay. So, there are two ways. One vibratory model will be to treat this shaft to be a flexible one, and therefore, the model that we developed just now or shown in the a while back is the appropriate vibratory model. But suppose that the diameter of the shaft is large enough, and our calculation suggests that this stiffness turns out to be of the order of 10 to the power 7 or so Newton per meter, then we will have to think twice whether this is an appropriate model. So, I may then find out the stiffness of the bearing, and the second model could be if the shaft is stubbier and quite rigid in that sense that it does not deflect as much and does not offer that much of compliance, then I may lump the rotor mass and shaft mass together, assuming that the shaft does not deflect, but in comparison the bearings may have comparable or lower level stiffness. Typically the stiffness of the bearing is definitely large, of the order of 10 to the power 7, not less than that. So, in such situation I may consider the bearing stiffness as one of the stiffness element, and then another alternate model I can have is this model. Going one step further, the third model could be that I will treat the shaft stiffness as one spring and the bearing stiffness as the other, and then combine these two springs in an equivalent stiffness. Okay. And we know how to combine two springs in series and two springs in parallel, and that becomes much more simpler way and more appropriate way if the shaft stiffness and bearing stiffness are not differing by an order of magnitude. Okay. So, typically it is said that if one stiffness is 10 times the other, it can be ignored, and with that logic you can have two different or maybe three different models depending upon what parameters are being evaluated. So, that is the reason why I said in the first time in the first discussion on vibration analysis that the first step of getting an appropriate vibratory model which actually represents the reality is quite challenging and takes a lot of your experience and expertise and understanding of that physical system, and so that of course has to be done with care. But once you get this kind of a model, subsequent analysis becomes straightforward and simpler. So, this is what one can start with a single degree of freedom system. Now, in addition to this discussion, I would like to also discuss little about what kind of vibration analysis that we can perform, or in the sense of types of vibrations or the modes of vibration, right. So, the example that we have been discussing of a wind turbine nacelle sitting on the column like this, we have seen that there will be a bending moment acting on it, there will be a twisting moment acting around the axis of the column, and then as this bladed rotor rotates, there would be a fluctuating vertical force which will cause force which is going to act axially, and longitudinal excitation will excite the column. So, as we discussed, there would be a mass of the nacelle which is quite heavy compared to the mass of the column, and then we can have the simplified vibratory model like this with the mass of the nacelle here and the stiffness of the column defined by the spring. And we all know that the stiffness of a circular bar like this is given by AE over L from our basic solid mechanics, cross sectional area times the modulus of elasticity over L becomes the longitudinal stiffness of the column, that gives you the Kc value. If you are interested in knowing how the nacelle vibrates vertically up and down. Okay. But if you treat the same system as a bending vibration case, that there is a mass sitting at the tip of this beam, and if this is vibrating laterally, which is quite possible the way the rotor rotates and the unbalance located at the radial distance r generates a moment, this is going to have the same mass being used here, and then you have this column acting like a spring having a lateral stiffness, and we all know that the stiffness K in such case is based on the flexural rigidity of this column. So, 3 E I by L cube becomes the stiffness of the column when it is executing a lateral vibration. Okay. So, I can still convert this same system in a different mode of vibration. So, now I am talking about a bending vibration, and so I can have the same spring mass system to represent the same physical system, but the mode of vibration is different. Then I can have the same system vibrating in a torsional mode. So, you have a column and then an inertia sitting at the top. This inertia is swinging about a vertical axis. So, it is going to have a torsional mode of vibration, and that torsional mode of vibration I can again model the same physical system like a mass and a spring. That spring will have its own stiffness, the torsional stiffness I can estimate that torsional stiffness, and we will take an example based on this physical system where T over J is equal to C theta by L. That is the standard expression we all know from the solid mechanics or strength of materials, and so T by theta of course then becomes the torsional stiffness for us. Okay. So, Kt or K theta is the torsional stiffness, and that becomes then C j upon L. Okay. So, the polar area moment of inertia comes into picture, the length comes into picture, and so based on all the parameters of this physical system you can estimate the torsional stiffness. The mass moment of inertia of this I will be known from the geometry of the nacelle, the mass distribution in the nacelle. So, all of that will give you torsional mode of vibration being investigated. So, the point here is just having one single mass does not mean there will be one degree of freedom or a single degree of freedom. Okay. You can have multiple degrees of freedom, and you can either combine them or you can treat them individually as long as they do not couple each other, and those things of course, we will see later, but the same physical system can exhibit different kinds of vibration, the longitudinal vibration, the torsional vibration, the lateral or a bending vibration, and so on. So, it is all up to us how do we model it. When we model it, we need to extract the required stiffness and inertia properties based on the dimensions or material properties. Obviously, as you see, the shear modulus comes into picture in the calculation of the torsional stiffness, and the Young's modulus appear in the other two, right. So, this is what we are supposed to do when we are trying to explore different kinds of vibration. So, another example is the wing of an aircraft. If we assume this to be rigid enough, then we can treat this to be a cantilever beam, obviously, right. So, you can have then this wing obviously as a cantilever beam, and this cantilever will undergo lateral vibrations based on either excitation from the flowing wind around it, or in addition you may also have excitation from the engine rotation. So, all of them will excite lateral vibrations. Of course, the wings are not as simple as simple constant cross section beam, but its cross section can have this kind of an aerofoil section, and then this cross section keeps changing along the length obviously. So, it becomes quite complex in that sense, but as a preliminary study one can estimate the natural frequencies of vibration for such kind of a wing structure. Another interesting thing that can happen is that this wing by its geometric properties and the excitation mechanism will not only have the bending vibration, but will also have a torsional vibrations. So, if the wind blowing across this structure will excite the twist, that means it can excite the torsion of this wing structure. In addition, you may notice very clearly that there is at the underside of this wing a turbine here, is not it. So, that turbine is going to generate a thrust, that thrust will have its own moment around this beam cross section. So, if you are treating this as the structure, the forces will generate twisting moment, and then apart from the bending vibration there would be a torsional vibration of this same wing. Okay. So, it is all up to us as to how and what we want to investigate it for, and maybe we should be needing to know all the different natural frequencies of a mechanical structure as we see here. Okay. Just a second. Okay. What else? I can give a couple of more examples. Now, I think we have done couple of examples of bending and torsion vibrations. Let us look at an alternate system, a ship propeller. Okay. A propeller shaft which is connected to engine here and has a thrust bearing, and then this propeller has is supported at different locations along the length, and these propeller shaft run in tens of meters long, and then the huge bladed disc here, which of course is responsible for the thrust for propelling the ship in the water. Okay. So, this is a very classic example of longitudinal vibrations. In this case, the vibrations along the longitudinal directions are quite possible, and of course, does not stop it from vibrating laterally as well, and So, you will need to then analyze and investigate the longitudinal vibration of this propeller shaft and maybe also a longitudinal vibrations, and these vibrations once estimated, the natural frequencies need to be kept away from the excitation frequency. So, the rotational frequency and its link with the natural frequency of vibration needs to be established to ensure that resonances are not set up anywhere. Otherwise, you all know what are the consequences of resonance setup, not only from our robustness or life viewpoint, but in this particular example it is the acoustic stealth viewpoint, it is very important. So, apart from the the acoustics generated because of the turbulence here in the operation of the propeller, the vibrating shaft will transmit their vibrations through these bearings to the hull structure. The hull itself will vibrate. The problem with the hull structure vibrating is that it has a very large surface area. So, a large surface area generating even a small vibration will send the signal out for the enemy ships or submarines to track where you are. So, from all of these viewpoint, ensuring that the operating speeds do not encroach into any of the resonances or natural frequencies of vibration is very important. If it is inevitable, then at least we should design the systems in such a way that the vibration generated do not transmit to the hull. So, the transmissibility comes into picture in this case. So, all of these are very important. So, first step obviously as we see here are modeling exercise. How do we model that? Okay. The other example of longitudinal vibration is a tappet valve mechanism. So, you all are aware of IC engines and how the tappet valve opens and closes to let the fuel into the cylinder here, and so it has a rocker arm which pushes the valve inside the cylinder against a spring here, and the camshaft which operates at half the engine speed pushes this push rod up for operating the rocker arm. So, in this case this particular push rod is typically long, and we can expect this push rod to vibrate in the longitudinal direction. So, apart from the vibratory system itself made of this rocker arm and the spring and then the valve, the push rod itself is can be a potential candidate for longitudinal vibrations. And so, depending upon the speed of operation of this cam, if it operates close to the natural frequency of the push rod, we can get in trouble here. Okay. In addition, it will be interesting to know what is the natural frequency of the spring, so that a phenomena called as the spring surge does not take place, the resonance in the springs is not set. So, all of these would need you to analyze this system for different kinds of vibration. So, what we have seen is through these variety of examples that the same system can exhibit different kinds of vibration. It could be torsional one, it could be longitudinal one, it could be bending one at the bending vibration, and for each of these we need to model the same system in a different way in terms of the parameters. Okay. Okay. Now, before we start deriving the governing equations, we can treat our simple single degree of freedom system to be like this. So, that means assuming that we have been able to convert our physical system into a simplified vibratory model like this, and have identified that the translatory motion x is the only degree of freedom here to be considered. How do we get the governing equations of motion. Okay. So, as the vibration analysis step number 2 of getting the governing equation from the vibratory model goes through a couple of alternate processes. The simplest one, as I mentioned, is of using a free body diagram for this mass, and I can have this m sitting here, which is isolated from its surrounding, and then if this is the positive direction x, x dot and x double dot, then obviously if this mass gets stretched to this new position here, so that it undergoes a stretch or movement x t, then the spring k gets stretched by a distance x, and therefore, by the very property of this spring, the spring will try to regain its original position, and therefore, the mass will be subjected to a restoring force, and that restoring force is going to be proportional to k, and therefore, restoring force will be proportional to the displacement through a constant of proportionality k, the spring rate. So, k x is obviously the restoring force that will act on this mass if it gets stretched by a distance x. Now, in addition, because there is a velocity involved, the dashpot has a property that it generates a the dissipating force acting opposite to the velocity, and therefore, if x, x double dot and x dot are positive rightwards, then obviously I can replace, or I can show the action or effect of this dashpot connected to the mass by a dissipating force acting opposite to the direction of velocity, and it is proportional to that velocity through a constant of proportionality c, that is the damping coefficient. So, c x dot is the force acting at the dashpot connecting point on this free body m, all right. And if we also include, although we are going to focus on free vibration response, but as a for the sake of completeness, maybe we include the excitation force, external excitation force F as a function of time, as a force acting on this mass. Then if we apply the Newton's second law here, then what we can get is that the set of forces acting on this mass in the direction of the acceleration equals mass times the acceleration. So, I can then write this as m x double dot equals all the forces. Now, these forces would obviously be f of t, because f of t acts in the same direction as the acceleration, whereas these ones are opposite to the direction of acceleration. So, I will have minus c x dot here and minus k x here, and then if I rearrange, I get our governing equation of motion, which you are quite familiar with as f of t. Okay. So, for all the simplified vibratory model later on, as you bring up in different context in representing different physical systems, once you have this, you first step will be to get the free body diagram and note all the forces which act on that free body, and then get this kind of a governing equation. Most of the times, as long as the system configuration is reasonably simple, Newton's law works very well, but as we go along, we shall also discuss how we can apply the energy methods to do the same, which turns out to be more elegant way, and for complex system, that is one of the common ones to be used. Okay. But let us stick to this method for the time being. Now, once we get this governing equation of motion, you can of course rearrange it in the form of x double dot plus c over m. So, dividing throughout by mass, you get this equation. On the right hand side, you now have the force per unit mass, and then as we will see shortly, the ratios of c over m and k over m are more commonly represented in another using other parameters which are commonly used. So, k over m you all know is the squared natural frequency of the system, and so you can get the same equation written in this particular form. Okay. So, c over m, of course, we shall shortly derive as we discuss damped vibration. It is given as 2 zeta omega n. Do not worry if you do not know this particular relationship, we are anyway going to derive it properly later on. So, if we represent c over m by 2 zeta omega n, this is another common form of the governing equation of motion. In this case, of course, it is all the terms are acceleration terms. The first term is of course acceleration. This equation is all force equilibrium of a vibrating body. Okay. So, this is a simple governing equation of motion of a single degree of freedom system, where the governing equation is obtained with the degree of freedom x. So, ultimately when you solve this equation, you are expected to get the solution in the form of response as a function of time, okay, subjected to forcing function f of t. Okay. So, before again moving ahead, I think it would be interesting again to have a look closer look at this governing equation that we have derived, or for that matter, before we start finding out the response of that governing equation of motion, we would like to have a relook at the elements of this simple vibratory system that we have been modeling, and what are the parameters of those elements of vibratory system. Okay. For example, most of the times in this particular topic, we are somehow going to convert our object object or a physical object into a simple vibratory model like this, comprising k, m and c. So, the element of this vibratory system are the inertia element, the stiffness element and the damping element, and the parameters are stiffness, mass and damping. So, what are these parameters? For example, in the example of a windmill or a wind turbine, what we said is, okay, this is a column on which the nacelle is sitting at the top. It was obvious to have this mass representing the mass of the nacelle. What is k representing? K is representing, if it is like a vertical vibration, a longitudinal vibration, then it is, this column is actually your stiffness element. Okay. And this, where is the dashpot? Dashpot does not appear here physically, but later on, as we will know when we discuss damping in more detail, that the very elastic deflection generates a dissipating force, and the dissipation mechanism in a stretched membrane, in a stretched body actually generates a damping effect, and therefore, the same column then acts like both a stiffness as well as a damping. Okay. But what are the these are the elements, but what are those parameters? How do I find k? How do I find m? How do I find c? So, that needs a closer relook, and incidentally it is time to understand what are the assumptions involved, and the governing equation of motion that we have derived, like mx double dot plus cx dot plus kx equal to f of t. In what context, in which cases is this equation valid, and is there any anything that we should be wary of or we should be mindful of while applying this equation to represent the actual physical system. So, in that context, this and couple of slides here we will discuss little bit more about it. So, this spring as I mentioned is the physical coiled spring which represents this particular stiffness. Now, what this stiffness is all about is that if I apply a force on this spring, we know very well that it will deflect, a deflected spring. So, if it deflects by a distance equal to let us say x, and if you are applying a force, then a finite amount of force divided by the finite displacement that it generates, that basically is your spring rate, okay, or the stiffness of the spring. And you can find this if it is physically a coiled spring, then you can actually get proper expression for K in terms of the coil diameter, the length, the number of coils and so on, that you have learned in a theory of machines as well as machine element design. So, this is valid because most of the times you have this force linearly related to deflection, or for that matter a deflection follows linearly to the applied force, which means that if I apply a 10 Newton force, the amount of displacement or a deflection in the spring is same if the ratio is same if I apply now 20 newtons, the amount of deflection will double. So, there is a linear relationship between force and deflection. So, in that with that logic Kx is our restoring force when a force is applied on such kind of an element, okay. Or I must say that the restoring force is directly proportional to x through a constant of proportionality k. That means, the force and displacement or deflections in the spring are linearly related, okay. And therefore, things become very easy for us because we are focusing on the vibratory deflection x of t, and no matter what x is, our restoring force will always be k into x. That simplifies the governing equation of motion, okay. However, so so k is equal to basically df by dk. You find out the slope of this curve, that obviously being a straight line, it is going to turn out to be a constant value. So, that is the stiffness of your system, okay. Now, however, there are issues in it, in the sense that we are all aware that in the example of this, the column is actually not a coiled spring, it is a continuously distributed system, it is a column, or it is a structure circular in cross section maybe, and it is not a coiled spring. So, we all know that if you apply a force, there would be areas where this stress induced and the strain are linearly related only up to a certain level, okay. After that, the linearity is lost, okay. So, on similar lines, in if it is any mechanical structure which has a compliance, there are situations where the linear relationship deviates that or is no more linear after a particular point. So, the linearity is lost, and you have a nonlinear relationship between the force restoring force generated with the deflection. That means, the change in the force value would not be the same for the equal increments in the deflection. So, this df by dx, which is the ratio or the slope of the curve between force and deflection, is continuously going to change. So, the stiffness is different here, the stiffness is different here, and the stiffness is different here. And therefore, what we actually do write this restoring force as linearly related to the deformation in the spring element is no more valid. It is not going to be only k into x, okay. So, such kind of a behavior is going to create the stiffness of the system as non-linear. I mean the restoring force is going to be a non-linear function of the deflection, and that is a major cause of concern in terms of formulating a governing equation of motion. Now, this is typically in the literature called as the hard spring behavior, where the restoring force increases non-linearly with deflection, deviates from a linear relationship, but you can expect this kind of a non-linearity in a practical element such as a bearing. So, it is possible to show that this bearing has a stiffness which is a function of the force itself. So, force deflection relationship is non-linear, and therefore, the way if I want to find out df by dx irrespective of how much is the value of x, that df by dx is constant k. So, the stiffness in a normal coil spring is going to be a constant value. So, that k is going to be the spring stiffness, and it does not depend upon how much force you apply here. So, therefore, that stiffness is a horizontal straight line. However, in case of machine element such as a bearing, it is beyond the scope to discuss why it happens, but it is true that the stiffness of a rolling element bearing or even the roller bearing is going to be a function of the force applied. So, the stiffness value of the stiffness depends upon the deformation or force, and therefore, depending upon at what force the system is being subjected to, the stiffness is going to be different. So, that means we cannot write this as k of x. You may have to write k as a function of x or f times x, and therefore, this proportionality element, that is k, is not a constant value, and therefore, the system governing equation is going to turn non-linear, because this is linear only when these coefficients are constants and you do not have powers of these variables and its derivatives. Okay. So, in this case the equation is linear, but the moment your k becomes a function of the dependent variable x, it becomes a non-linear equation. So, the question is, or this is of course the case with the ball bearings. If you treat an elastomer as your mount, so instead of a coil spring, sometimes you use mounts which are made of polymeric material. Those mounts, if they are rubbery material, then it will have a slightly different force deflection relationship. It is typically may have a softening kind of a behavior to start with. Of course, in many cases this becomes like that, but in this range it becomes a softening kind of a element, and then but the point is that it still becomes non-linear beyond this particular displacement value. So, the question now is that if the most elements here, if they show this kind of behavior, how can we rely on the governing equation that we have derived here, mx double dot plus cx dot plus kx equal to 0. We have been seeing this equation being used everywhere, and all the entire theory has been based on these equations. So, then the question is, on what basis are we allowed to use these simplified linear governing equation of motion. Okay. So, two things here. One is, most vibratory systems would have amplitudes of this vibration typically of the value or level that falls well within this range, which means that rarely do we have systems going into vibration amplitudes way beyond this limiting value, and therefore, the restoring force becoming nonlinear does not arise at all. That means, most of the times the amplitudes are well within a small amplitude range, and that is the reason why you would find a string attached to this particular equation which has been derived. This is based on the assumption that the amplitude of vibration is small, and that small actually has a lot to do with this particular range. Okay. And so, small amplitude vibration, because that small amplitude vibration pertains to this range of linear force deformation or force deflection relationship, it is perfectly valid to assume a restoring force which is directly proportional to x and k being constant, and therefore, the small amplitude vibration takes care of linear vibration analysis. And therefore, although it is true that it is valid for small amplitude vibration, and you can definitely use this equation for your preliminary analysis. However, if your f of t is such or your parameters are such that the estimated x turns out to be much larger in amplitude, you should come back here and check whether it is going into a nonlinear regime, and if it does go into this regime, then you should come back to this equation and reformulate it with the restoring force being formulated as a nonlinear restoring force, and there are equations which govern the behavior in this region, and that should be used to evaluate the response. Okay. Fortunately, as I have mentioned, that most mechanical systems vibrate with amplitudes far less than this limiting value, and therefore, we are all the time most likely to work in a linear regime, and therefore, k into x is the safe bet, and you can actually use that expression in the governing equation. However, the whole purpose of telling you this is to highlight what are the assumptions involved in deriving these governing equations of motion. As long as you are mindful of that, it's okay, but keep in mind that you can get into nonlinear regime, and then these simplified expressions can give you incorrect answer. Okay. So, you can get started with a linear assumption, but you will have to sooner or later ensure that your yeah. So, you will have to take care of this part appropriately. Okay. Now, in addition to this spring element, which gives you the first parameter as the stiffness of the system, you also have a damper here or a dashpot. As you can see, a piston which is inside the cylinder, and that cylinder is filled with a viscous fluid which creates a drag whenever the piston reciprocates inside the cylinder. There is a slight clearance here between the cylinder internal surface and the piston outer surface, and that small clearance, a viscous fluid separates the two, and during the motion it creates a dissipating force, and that is responsible for a dissipating force which is appearing here as Cx dot. Now, here also we should be clear that this dissipating force is linearly related to velocity of the moving elements. So, the relative velocity x dot gives you the dissipating force F. So, they are linearly related here, and the slope of x F versus x dot is a constant value, and therefore, that slope here is going to give you C. So, tan of this angle alpha gives you the constant of proportionality, the C, the damping coefficient. Here the tan of this alpha gives you K, here it gives you the damping coefficient. Okay. Again, in case of practical systems, the damping or the damping related dissipating force is even highly nonlinear even in the initial range, right. So, for example, if there is no dashpot here, for example, if the vibratory system is moving in a fluid, or if there is an aerodynamic forces which are acting on this mass, the force versus x dot relationship is not a linear one. It can take this form where n could be as high as 7/5 or so. So, such kind of relationship between the dissipating force and the velocity term x dot can be highly nonlinear here, and therefore, what value of c will you use? So, c will be different at different velocity values. So, if you are operating at this velocity, the c will be the slope at this point. If you are operating at this velocity, the value of c will be the slope at this point, and which actually means that the dissipating force is actually dependent on x dot, because if it cannot be F is equal to C x dot, it is going to be F is equal to C x dot to the power n, and therefore, actually the coefficient C is going to be a function of the velocity value. Okay. Now, this is about the damping. In fact, this is one of the most complex parameter of a vibratory system to estimate, and the curve that I have shown here you here is actually an approximate value, but actual damping can be complex for the simple reason that there is no single mechanism which creates dissipation in a typical vibratory system. There are multiple contributing phenomena which contribute together in their different ways to create a total dissipating force, and the mathematical expressions capturing those phenomena can be quite complex in nature, and therefore, damping as a parameter is established or is acknowledged as one of the most complex parameter to actually capture and formulate. But there is a reason why in most preliminary vibration analysis this dissipating force, the formulation of the dissipating force as C x dot or as a force which is dependent on only on velocity through a constant C, is one of the most common and preferred one for variety of reasons, and I will discuss that later. But this is mathematically this actually an assumption that makes our life easier for the mathematical simplicity. The analysis process is well defined in that case, and the governing equations of motion stays linear. That is the most important advantage that we get, because the mathematics becomes much easier for that particular reason. And the second important reason for that is something which I will discuss once we discuss the forced vibration case. Okay. So, these two are the most important parameters of the vibratory system. The third parameter is very obvious, and it is by far the most simple parameter or element to consider in a modeling exercise, because mass is very simple to estimate even if the system is complex. These days through your solid models you can get all the mass and inertia, mass moment of inertia properties, and so it is very simple that way. But however, the way we have shown all these parameters as the slopes of force versus deflection or force versus velocity graph, inertia also is nothing but the slope of force, fictitious force, the inertia force versus acceleration. So, this angle alpha, tan of this alpha is your inertia, okay, and the equation involved of course is F is equal to mx dot. So, m is a constant of proportionality, and therefore, for all our mechanical systems the mass is obviously going to be a constant value, and that basically is one of the simplest parameter, and usually we get all the complexities in the modeling exercise and solution process through the damping element, relatively less with the stiffness element, and usually literally nothing with the mass element. So, stiffness is easier to get, damping is more tedious, and unless we make simplifying assumptions, and the mass is the simplest of all. Now, if you believe and think that in vibratory system the mass or inertia property does not change, you can be in some surprise. Actually, there are very few cases where you do get mass changing as a function of time or as it operates, but we can still have a look at this example where the inertia property is actually changing every time. The example I am taking is of a simple IC engine where and a flywheel can be treated like a huge mass which can be treated fixed, and this shaft can be treated as your stiffness element, and this entire mechanism, crank, connecting rod and piston itself is your inertia in a torsional vibration setting. This entire mechanism itself is like a inertia at the tip of this crankshaft, right. So, one can find out what is the stiffness, but when you look at the inertia, this is a mechanism which has a moving piston and an oscillating and rotating connecting rod and a crank here. So, the way to find out the inertia is to find out the kinetic energy of individual elements and find out an equivalent inertia, and we all know that the velocity of this piston and the velocity of this connecting rod at these positions are going to be changing each instant of time. So, the kinetic energy also fluctuates, and so the equivalent inertia that you can find will also change with time, and therefore, you cannot have a direct linear relationship between the inertia force and the acceleration. So, the inertia property of such IC engine mechanism or connecting crank connecting rod and piston mechanism is not going to be a constant, although we can integrate the kinetic energy over one cycle of rotation and equate it to a constant I value, which is going to be an equivalent constant I, but strictly speaking it is going to be a function of angle, and therefore, will be function of it is not going to be a constant value as such. So, these are all various parameters of the vibratory system that we discussed: stiffness, damping and inertia, and those are the main elements of any vibratory system. Once they have been defined and found, the stage is set for the analysis of this linearized governing equation of motion. What we discussed is that inherently the stiffness, damping are nonlinear, but we linearize them, and we linearize for one simple reason, that the amplitudes of vibrations, if they are small, this assumption of linearity is actually quite valid in that sense, and particularly for this particular force, this mostly 99% of the cases or plus we have it m as constant value. So, it is absolutely no problem in terms of the linearity assumption. It is only when we look at the damping only for idealized viscous damping case. In fact, that also is valid for the relationship of the dissipating force and the velocity, or the velocity, relative velocity between the two separating surfaces, where we apply the Newton's law of viscosity. All the assumptions which are required to be valid in those cases will be the assumptions for getting this as a constant force only dependent on x dot as one of the assumption here. So, what is important is that the velocity gradient in the separating two surfaces, the piston surface and the cylinder surface, this velocity gradient is a linear one. All of those assumptions which we know, if they are valid, then only this equation is valid or this term is valid, right. So, for those ideal viscous dashpot assumption, the damping is constant, but otherwise not. But for reasons which will be clear little later, I will come back to this particular term. We always approximate the damping, and it is really from engineering viewpoint not necessary to get deeper and generate complex nonlinear governing equations, generating more accurate solution. Most of the times we are always vying for responses which are accurate from the engineering perspective, and they should be we are only interested in getting quick workable practical solution of these vibratory systems. So, very accurate solution may not be relevant or important. So, from all practical viewpoint, damping is treated like C x dot, and C can be treated as constant. Okay. But these are all the reasons, and I discussed these points so that you are aware that these are the underlying assumptions on the basis of which you are solving these equations, and as long as you know that these are the limitations of this model, it is okay and it is fine. Okay. In this lecture, what we discussed is broad contents of this course, what are the various topics. We also looked at how a single degree of freedom system model is formed from a given physical system, how the governing equations of motion were obtained, and more importantly the elements of a vibratory system, what are the parameters associated with a vibratory system, within what conditions the governing equation of motion is valid, right. So, the main takeaway was the basic assumption in all the cases that we will deal with is the small amplitude vibration assumption, which means that the amplitudes of vibration are small enough that the elements are or the parameters of the vibratory system are considered constant. Okay. So, we will stop here, and then in the next lecture we will continue solving our basic equation and try to figure out how to find the response of such simplified vibratory system to some initial conditions, and from that move on.